Hello, linear algebra students. This video lesson is on two distinct topics, diagonalization and QR factorization. We'll begin with diagonalization. A square matrix A is diagonalizable if and only if there is an invertible matrix P and a diagonal matrix D for which the following holds true. So you begin with the matrix A and you multiply it on the right by this invertible matrix P and then on the left by its inverse. And if this produces a diagonal matrix, then we say that A is diagonalizable. Now, if A is diagonalizable, then the diagonal entries of D are the eigenvalues of A, and the columns of P must be linearly independent eigenvectors corresponding to those respective eigenvalues. This means that if A is n by n, then all of the matrices involved here will also be square and n by n, and the matrix P must be constructed by using n linearly independent eigenvectors. Well, as we've seen in the past, sometimes when you have a repeated eigenvalue, the repeated eigenvalue does not have as many linearly independent eigenvectors as its multiplicity. That can happen. So if an eigenvalue is, say, repeated 3 times, it may only have one linearly independent eigenvector. But in order to have enough linearly independent eigenvectors to be diagonalizable, this would require that each repeated eigenvalue with multiplicity k, that these eigenvalues have corresponding eigenspaces with dimension k. So if an eigenvalue is repeated 3 times, we would need that eigenvalue to correspond to 3 linearly independent eigenvectors in order to produce enough eigenvectors to create an invertible square matrix P. Thus, a square matrix A is diagonalizable if and only if the multiplicity of each eigenvalue equals the dimension of its corresponding eigenspace. And this will certainly be the case if all the eigenvalues are distinct, because if an n by n matrix has n distinct eigenvalues, then each eigenvalue will correspond to a one-dimensional eigenspace. There will be one basis vector required of the eigenspace. So the dimension would be 1, which would match the multiplicity, and that would be true for all the eigenvalues and corresponding eigenspaces. Okay, let's explore some of these ideas. If possible, diagonalize each matrix below. Use technology to find the eigenvalues and bases for the eigenspaces. In this first case, I use an eigenvalue calculator to get the following eigenvalue-eigenvector pairings. The two eigenvalues are distinct, so they correspond to one eigenvector each to form a basis for its eigenspace. And we learned in previous lectures that eigenvectors corresponding to different eigenvalues are guaranteed to be linearly independent, which is clear in this case. Neither vector is a multiple of the other. Thus, this matrix is diagonalizable, and we can construct the invertible matrix P by putting these eigenvectors as its columns. The diagonal matrix D will have on the main diagonal the eigenvalues, which are 1 and 2. And this is a diagonal matrix, so it should have zeros everywhere else. Now, one thing you have to be careful about is the ordering in which you place the eigenvalues on the main diagonal. If the first column of the matrix P was an eigenvector, V1, associated with eigenvalue R1, then you must make sure that the main diagonal entry in the first column is R1. So the columns of P must align with the columns of D as far as the eigenvector-eigenvalue pairings. And then since we put V2 in the second column of the matrix P, we got to make sure that R2 is on the main diagonal in the second column of the diagonal matrix D. So you do have some options. If you choose to switch the order of the columns of P, then make sure you also switch the order of the placement of the eigenvalues on the main diagonal of D. So this eigenvalue and this eigenvalue need to switch places. And these would also be acceptable choices of the matrices P and D. But let's go back to the original and continue with the diagonalization. Once we have established a matrix P, you must find its inverse. I use technology to find that inverse. And once we have its inverse, we put the matrix A in between the inverse of P and P. And then this product on the left, P inverse times A times P, will be equal to this diagonal matrix D. So this is one option for diagonalizing the matrix A. Just to present a second option, if we construct the matrix P by switching its columns, then we got to make the necessary adjustments to the matrix D, find the inverse of this new matrix P, put the matrix A in between, and then this product, P inverse times A times P, will also produce that diagonal matrix shown here. And this is a second option. I leave it you to confirm both of these statements. Now let's look over at matrix A2. Using technology to find the eigenvalues, in this case we get a repeated eigenvalue. We get the r's are both 1, so the multiplicity is 2. And when you find the corresponding eigenspace, you only get one basis vector in this case. Hence, we only have one linearly independent vector. One such basis vector is 1, -1. You should be able to confirm all of this information by hand. But here's a case where we have a multiplicity of 2 for the eigenvalue, but we have a corresponding dimension of an eigenspace that is only 1 because there's only one vector in the basis. Therefore, we are not able to find two linearly independent eigenvectors to use to construct the columns of the matrix P. And since we need P to be invertible, I can't use two linearly dependent eigenvectors as the columns of the matrix P, because a matrix P with two columns that are linearly dependent will have a determinant of 0 and will not be invertible. So because we had an eigenvalue whose multiplicity did not match the dimension of its corresponding eigenspace, this will disqualify A2 from being diagonalizable. Okay, let's go to the next page and analyze some 3x3s. Using technology on A1, we find that it has 3 eigenvalues. One of them is repeated. The first eigenvalue is -1, and it has a corresponding basis vector for its eigenspace of 0, 1, -1. However, the next two eigenvalues, R2 and R3, are both 2. And when you find a basis for the corresponding eigenspace, we are only able to find one linearly independent eigenvector. This is a basis vector, so any multiple of it is also an eigenvector, but if you take any two eigenvectors from the space, they are multiples of each other. They are not independent. So here we had a multiplicity of 1 and a dimension of an eigenspace of 1. So this eigenvalue poses no barriers to the diagonalizability of the matrix. But for the second eigenvalue, this is where we have the issue. The multiplicity is 2, but the dimension of the eigenspace is still only 1. So this eigenvalue prevents this matrix A1 from being diagonalizable. And that's because we need a total of 3 linearly independent eigenvectors in order to construct the matrix P. This P must be a 3x3 matrix, so it requires 3 columns that are linearly independent, and it can't be done in this case. Using technology on A2, we find it has a distinct eigenvalue, R1 equals 4, with a corresponding basis eigenvector of 1, 0, 1, or any non-zero multiple of this vector would also work. Then matrix A2 also has a repeated eigenvalue. Both R2 and R3 are the value 1, but this time we are able to find 2 independent basis vectors. Vector V2 is the vector -1, 1, 0, and we can get another vector, we'll call it V3, which is -2, 0, 1. So we had a multiplicity of 1 and then a dimension of the eigenspace 1 for the first eigenvalue that matches. Then we had a multiplicity of 2 and a dimension of 2. So we have enough linearly independent eigenvectors to diagonalize this matrix. Let's let the matrix P be equal to a matrix whose columns are these eigenvectors, and in the order that we found them. So the first column is vector 1, second column vector 2, and third column vector 3. This will dictate what the matrix D will look like. Since the first column of P was an eigenvector corresponding to eigenvalue 4, then the 1, 1 position of this diagonal matrix needs to be 4. The second column and third column were eigenvectors corresponding to the repeated eigenvalue 1. So the second and third column on the main diagonal will have the 1s, and then 0s everywhere else. And this is our matrix D. Now we find the inverse of this matrix P. I use technology to do that, and I get the following. Now this inverse has a lot of fractions in it, so commonly what's done in such a case is to identify the least common denominator and then factor out that denominator. So in this case, we could write this inverse matrix as 1/3 of the matrix 1, 1, 2, 0, 3, 0, and -1, -1, 1. This will make multiplication of matrices a little bit easier if the fractions are factored out. So we will use this for our inverse matrix. And now in between P inverse and the matrix P, we have the matrix A. And we have a diagonalization of the matrix A. We take the matrix A, we multiply it on the right by this invertible matrix P, and then on the left by its inverse, and this product will equal this diagonal matrix D, whose main diagonal entries are the eigenvalues of A. Now this is just one option here. Like before, we saw that we could take these three eigenvectors and reorder them. That would have the effect of reordering the entries on the main diagonal of D accordingly, and of course would change what our inverse matrix is. And also we can use any non-zero multiples of these basis vectors as our columns of the matrix P. For example, as another option, for the first column of a matrix P, let's do a doubling of vector V1. That gives me a column of 2, 0, 2. So any non-zero multiple of V1 will work. Any non-zero multiple of V2 or V3, the same. So I'm going to do negative V2 and negative V3 as my next two columns. That gives me 1, -1, 0 as the middle column, and 2, 0, -1 as the third column. And I will use this for my matrix P. Next, we determine what the matrix D will be. Well, the first column is still an eigenvector corresponding to the first eigenvalue, the distinct eigenvalue of 4. So we still put a 4 in the 1, 1 position. And the next two vectors are still vectors that correspond to the eigenvalue 1. So the main diagonal in this case does not change when compared to the main diagonal of the diagonal matrix we had right here. So this is another pairing that will be acceptable for an invertible matrix P and a diagonal matrix D. Now the inverse of this matrix P will be as follows. And then the matrix A goes in between the inverse of P and the matrix P. So here is another way to diagonalize the matrix A. And I should say that both of these are really the matrix A sub 2, referring to this matrix here, A sub 2. So this shows us that in reality, there are infinitely many possible ways that you can diagonalize a matrix that is diagonalizable. You simply vary what kinds of multiples of your basis vectors you're going to choose to use to construct your matrix P. Okay, let's go on to the next page. Now, given the diagonal matrix below, find the indicated powers and generalize your findings. So we have a diagonal matrix, and when we do a D squared, that's going to be the matrix D times itself. And we do matrix multiplication. The first column will be -1 times -1, which is 1, and then 0, 0. The second column will be 0, and then 3 times 3, which is 9, and then 0. And the last column will be 0, 0, and then 2 times 2 is 4. Notice that each entry on the main diagonal of this result is the square of the entries on the main diagonal of the matrix D. If I do D cubed, that's going to be the same thing as doing D squared times D. I've already computed D squared, multiply by D, and we're going to get a new matrix. The first column will be -1 times 1, which is -1, and then 0, 0. Then we'll get 0, 9 times 3, which is 27, 0, and then 0, 0, and 4 times 2 is 8. You can already pick up on the pattern, I'm sure. D to the fourth will be D cubed times D. I've already calculated D cubed. Multiply by one more copy of the matrix D. This will produce a new 3 by 3. First column will be -1 times -1, +1, 0, 0. Then 0, 3 times 27 is 81. And then 0, and then 0, 0, and 2 times 8 is 16. Well, this 1 here is just -1 raised to the fourth. This 81 was just 3 raised to the fourth. And this 16 in the end was 2 raised to the fourth. So basically, if you take a diagonal matrix and raise it to a power, you simply have to raise each entry on the main diagonal to that power. So as a generalization, D raised to the n will wind up being -1 raised to the n as the 1, 1 position, 3 raised to the n in the 2, 2 position, and then 2 raised to the n in the 3, 3 position, and zeros everywhere else. And this finding is summarized in this statement here. Note that raising a diagonal matrix to a power results in raising each main diagonal entry to that power. All right, let's see how this might be useful in the next page. If A is diagonalizable, then powers of A can be computed as follows. So we'll begin with the assumption that A is diagonalizable, so we can find a matrix P and a matrix D, where P is invertible and D is diagonal, that satisfy this statement. I can effectively solve this equation for the matrix A by multiplying on the left by P and on the right by P inverse, and do that to both sides of the statement. And then, of course, P times its inverse will be the identity. So you get a couple identity matrices here, an identity matrix and another identity matrix. So all these identity matrices times A will just be the matrix A. So A is effectively isolated. And on the other side, we have the matrix P times the diagonal matrix D times the inverse of the matrix P. So we can solve for A and write A this way. Thus, we can think of this as a factorization of A. We've taken A and expressed it as a product of three matrices. Okay, so let's see how this can be helpful. The matrix A below is diagonalizable. Find the indicated powers of A. So we have this matrix A, and it is diagonalizable. In fact, this is the same matrix that we had on the last page. So we can find a diagonal matrix D and an invertible matrix P such that this matrix is equal to P times D times P inverse. Thus, if I want to do A squared, I simply have to do P times D times P inverse times itself. P times D times P inverse. And by the associative property of matrix multiplication, now keep in mind, we cannot switch the ordering of the matrices. Matrix multiplication is not commutative. So what I can't do is I can't take this matrix P and move it over here. Not allowed. But what I can do is change the order in which I do the multiple operations of multiplication here. In other words, I can insert parentheses where I'd like. So I can do this product here in the middle first. And of course, that's the identity matrix. So this winds up being P times D times another D times P inverse, which is just really P times D squared times P inverse. And watch what happens when I try to do A cubed. So here's the matrix A written 3 times. We have P, D, P inverse written 3 times. And we have several instances of P multiplied with P inverse. So we get the identity matrix twice in here. So in the end, this winds up just being the matrix P times D times D times D, or D cubed, times the inverse of the matrix P. So we can see a generalization occurring here. If A is diagonalizable, and I want to find a high power of A, then I can simply do the following. A to the 10 will be the matrix P times the diagonal matrix D, but raised to the 10, and then times the inverse of the matrix P. Now this was the matrix A from the last page, so I've already figured out some choices for the matrix P and the matrix D. And one such choice was the matrix P is 1, 0, 1, negative 1, 1, 0, negative 2, 0, 1. This corresponded to a diagonal matrix that had 4, 1, 1 as the main diagonal. That will now be raised to the 10th power. And then the inverse of this matrix P was 1/3 of this matrix. So we have the matrix P, this is the matrix D being raised to the 10th power, and this is the inverse matrix here on the right. Well, this 1/3, we can factor it through all the matrices to the very front. So it's convenient to be able to do that and leave the fractions off until the very end and do all your matrix calculations without fractions. Also, we have here in the middle, we have a diagonal matrix raised to a power 10, which we've learned that we can just raise each of these entries along the main diagonal to the power 10. So we'll have 4 to the 10, which will be a large number. We'll just leave it as 4 to the 10. 1 to the 10, which will just be 1, and 1 to the 10, which will just be 1. So I can rewrite this product as follows. 1/3 has been written out to the front, and the diagonal matrix in the 1, 1 position is 4 raised to the 10. The other two matrices I've left alone. Be careful you do not switch their ordering. You are not allowed to move this matrix over here, for example. You have to leave the matrices in this order. But we can multiply them in any order, meaning I could do this product first, or I could do this product first. Let's do this product first. So we have this 1/3 in the front still, and you multiply these two matrices using matrix multiplication, and we get the following result. So the first column will be 4 to the 10, 0, 4 to the 10. The middle column will be negative 1, 1, 0, and the third column will be negative 2, 0, 1. And then we still have this matrix here on the right. Leave the 1/3 out, and let's go ahead and multiply these two matrices together next. We're going to get in our first entry 4 to the 10 plus 2, then 0, and then 4 to the 10 minus 1. And this is just our first column. The middle column will be 4 to the 10 minus 3 plus 2, so minus 1, then 3, and then 4 to the 10 minus 1. And the final column will be 2 times 4 to the 10 plus 0 minus 2, and then 0, and then 2 times 4 to the 10 plus 1. And now I'll finally reach for a calculator and calculate all these terms, and then multiply the entire matrix by 1/3 as a final step. And in the end, we get this 3 by 3 matrix. 349,526, 0, 349,525 is the first column. And then the other columns are as follows. And this matrix is the result of raising a to the 10th power. Now, why would we want to do this instead of just raising a to the 10th power? Well, as matrices get larger and powers are extremely high, it takes a lot less computing to diagonalize the matrix first, if possible, and then to perform the calculations required to undergo this process. Okay, and let's go to our last page. Now this page is about QR factorization, which is the second topic of this lesson. And we just have one page dedicated to what this is. Now a matrix A that is m by n with linearly independent columns can be factored A equals QR, where Q is also m by n, and whose columns form an orthonormal basis for the column space of A, and R is n by n, so square, and upper triangular. And we call this a QR factorization of A. Find the QR factorization of the matrix below. Now this matrix is 3 by 2. It has 2 columns. We'll call them vectors u1 and u2. And notice that neither vector is a multiple of the other. So these are linearly independent vectors. So if we were to find a basis for the column space of this matrix, we would need both columns in that basis. Now the matrix Q that we're after is also going to be a 3 by 2 matrix, but we need the columns to be an orthonormal basis for the column space of A. So if we think of u1 and u2 as a non-orthogonal, non-orthonormal basis for column space of A, then all we have to do is convert this to an orthonormal basis using the Gram-Schmidt process. And recall, to say orthonormal means that we need 2 vectors that are perpendicular to each other, that still span the same space as these 2 vectors, u1 and u2, and whose magnitudes are 1, so they need to be normalized. Well, this is a 2-step process, if you recall, from our lesson on the Gram-Schmidt process and finding orthogonal and orthonormal bases. So first we will focus on finding an orthogonal basis. So v1, we can let it just be equal to u1. This is the first step of the Gram-Schmidt process, so 1, 0, 2. And refer to our notes for finding how to compute the second vector. We're basically going to project u2 onto u1 and then find the orthogonal component. And the formula was that vector v2 can be constructed by doing vector u2 minus, and then we do a dot product of u2 with v1, divide by the dot product of v1 with itself, and then multiply this by the vector v1. So in this case, let's do these 2 dot products. We have vector u2 minus, now u2 dot v1. Well, v1 is the same thing as u1, so I really just need to do the dot product of this vector and this vector. So multiplying corresponding entries and adding together, we get 0 plus 0 plus 2. So we have a 2 in the numerator, and then we're going to dot v1 with itself. Well, v1 was the same thing as u1. So we'll just do this vector dot with itself. So square the entries and add together. So we get 1 squared plus 0 squared plus 2 squared, and we get 5. So we have to remove 2/5 of v1 from u2. That winds up producing the following vector: negative 2/5, 1, 1/5. And when there are fractions involved like this, it's helpful to factor out that common denominator. So we'll have factor out a 1/5 and say 1/5 times the vector negative 2, 5, 1. This is our v2. So v1 and v2 are orthogonal to each other. If you do their dot product, you will get 0. But they are not unit vectors yet, so we need to normalize them next. So we've got to find their magnitudes. Let's go with the magnitude of v1. Take the square root of the sum of the squares of the entries. So 1 squared plus 0 squared plus 2 squared, that's 5, and take the square root. So radical 5 is the magnitude of vector v1. So this allows me now to construct a normalized version of it we'll call vector w1. and we'll do 1 over radical 5 times the vector v1, which was 1, 0, 2. And here is our w1. Let's go ahead and leave that 1 over radical 5 factored out, at least for the time being. Let's find the magnitude of the second vector, v2. So v2, if we look at this version of v2, we have a scalar times the vector. So we really just need to find the magnitude of this vector and then multiply by that same scalar. So it's going to be 1/5 of, and then we do the square root, square the entries that you see right here. So square -2, square 5, square 1, add together. That gives us 30. So 1/5 of radical 30 is the magnitude of vector v2. So we can construct our normalized vector w2 by doing 1 divided by this. So we'll have 5 over radical 30, the reciprocal of the magnitude, and then times the vector v2. Well, the vector v2 was 1/5 of the vector -2, 5, 1. And you can see this simplifies nicely. The 1/5 and the 5 cancel, so we just get 1 over radical 30 times the vector -2, 5, 1. Notice we could have got this result simply by beginning with v2 and scaling it by 5. That gets rid of the 1/5 to create the vector -2, 5, 1, and then normalizing that vector instead. And that in one nice clean step would take you to this expression. So w1 and w2 form an orthonormal basis for the column space of the matrix A. w1 and w2 are orthogonal to each other. If you dot product them, you will get 0. And their magnitudes are 1 each. We construct the matrix Q out of this orthogonal basis. So we'll put vector w1 in the first column and then vector w2 in the second column. So at this point, it becomes maybe more convenient now to take these scalars and to distribute them through the components. And we'll do the same thing where both these radical scalars and distribute through the components. Otherwise, it can get quite clunky looking inside this matrix. So the w1 vector we'll put as the first column. It's going to be 1 over rad 5, then 0, and then 2 over rad 5. And then the w2 vector will be -2 over rad 30, 5 over rad 30, and 1 over rad 30. And this forms our Q matrix. Okay, we're partway there. We still have to figure out what the R matrix is so that we have a complete QR factorization. Now, in a previous lecture, we had talked about if you have a matrix whose columns are orthonormal, it turns out that that matrix, when you multiply it with its transpose, it'll produce the identity matrix. So this matrix Q does have orthonormal columns. So we know that Q transpose times Q should also equal an identity matrix. We're going to compute Q transpose times Q. So the matrix Q transpose, so this first column of Q will become the first row of Q transpose. So you have 1 over rad 5, 0, 2 over rad 5. And then the second column of Q will be -2 over rad 30, 5 over rad 30, and 1 over rad 30. And now we're going to multiply this by the matrix Q and confirm what happens here. Now let's look at the dimensions. Q transpose is 2 by 3. Q is 3 by 2. So I do expect to produce a 2 by 2 matrix out of this. Let's see what that matrix is. So we're going to multiply this entry and this entry. That's going to give me 1/5. Then multiply these two entries will be 0. And then multiply these two entries. That'll give me 4/5. And we add together. This will be the 1, 1 position of my 2 by 2 matrix result. Now let's compute the 2, 1 position. So we're going to multiply this entry by this entry. That'll be -2 over rad 150. Then multiply this entry and this entry, which will be 0. And then multiply these two entries, which will be +2 over rad 150. And that is the 2, 1 position of our product. All right, let's now work with the second column of Q. We will multiply this entry and this entry. So that'll be -2 over rad 150. Then multiply these two entries, which will be 0. And then multiply 2 disappeared from that numerator. Put that back. And then multiply these two entries, and we get 2 over rad 150. And that completes the 1, 2 position. And now finally, we will multiply these two entries. That gives me 4/30. These two entries multiplied gives me 25/30. And these entries multiplied give me 1/30. And then simplifying all of this, we do in fact get 1, 0, 0, 1. We get the 2 by 2 identity matrix. Now this was a little bit tedious calculation to confirm something so simple. But when you think about it, this is a totally expected result. When I multiply this column to this row, It's basically like doing a dot product of that vector with itself. But since these vectors are unit vectors, when you dot product a unit vector with itself, you get the square of its magnitude. Well, its magnitude is 1. So when I dot product the two orange highlighted vectors, you get 1. But when I dot product these two vectors, they're orthogonal to each other because the columns of Q formed an orthonormal basis. So it's totally expected that when you do the dot product of these two orange vectors that you're going to get 0. So we confirm that we get a 1 and then a 0. And now let's dot product these two vectors. Well, these two vectors currently highlighted are orthogonal, so we do expect to get this 0. And then finally, when I dot product these two vectors, this is just the vector dot product with itself, and it's a unit vector, so we get the square of its magnitude. Its magnitude is 1, therefore we get this final 1 here. This is why when you take a matrix Q and multiply it with this transpose in any order, that in the end you're going to get an identity matrix. Now, this is a very useful fact because we know that we want our matrix A to factor as QR, and we already know Q, but we don't know R yet. But I can solve this equation for R by multiplying both sides on the left by Q transpose. That gives me Q transpose A has to be equal to Q transpose times QR. But we just confirmed that when you multiply Q and Q transpose that you get the identity matrix. And the identity matrix times R is just R. So in other words, we can calculate R now by doing Q transpose times the matrix A. So here's the matrix Q transpose, and we'll multiply it now by the matrix A and perform this matrix multiplication. All right, so effectively we're going to do the dot product of this vector with this vector. That gives me 1 over rad 5 plus 0 plus 4 over rad 5. That'll give me 5 over rad 5. Now we'll dot product these two vectors. We get negative 2 over rad 30 plus 0 plus 2 over rad 30, which gives me 0. This isn't surprising because the two orange vectors are orthogonal to each other, because 1, 0, 2 is just a scalar multiple of this row, and the two rows of QT are perpendicular to each other. Therefore, the two orange vectors are still perpendicular to each other. We get that dot product of 0. All right, so there's our first column. Now we'll basically do a dot product of these two vectors. We get 0 plus 2 over rad 5. So we get 2 over rad 5. And now dot product these two vectors. We'll get 0 plus 5 over rad 30 plus 1 over rad 30. That'll give me 6 over rad 30. And this is our R matrix. Notice that it is upper triangular. Thus, our conclusion is that we have found a way to factor the matrix A into a matrix Q, whose columns are orthonormal, times a matrix R that's square, and that is upper triangular. Here's our matrix Q, here's our matrix R, and I'll leave it to you to verify that when you multiply these two matrices, that in the end we do get the matrix A. So you may ask yourself, what is the purpose of doing a QR factorization? Well, QR factorizations will simplify certain calculations that computers need to do with matrices when the matrices are large. Also, it provides a theoretical way to approximate eigenvalues when the roots of the characteristic polynomial are not rational numbers. However, we will not discuss these applications at this time. Instead, we just focus on how to find the QR factorization. And this wraps up our lesson on both diagonalization of a matrix and also the QR factorization of a matrix.